Hello everyone, I am Chong from Zhejiang University. I am here to present our work, FreeEagle, a data-free detector against the complex neural Trojans. Backdoor attacks against the deep neural networks is a typical threat to artificial intelligence. This kind of attack is also known as neural Trojans. A typical way to inject a backdoor into a deep neural network is to poison the training dataset. For example, adding triggers to some training samples and mislabeling them. After being trained on the poisoned dataset, the backdoor model will misclassify samples with a particular trigger into one attack chosen class. While for samples without the trigger, the backdoor model will behave normally and correctly classify them. Training deep neural networks requires a large amount of computational resources, so it is common for users to download models from model sharing platforms such as ModelZoo and GitHub. However, a malicious model provider may upload a Trojan model to the platform without uploading any validation data. In this scenario, if the platform maintainers want to check whether the uploaded models are safe, they should build data-free Trojan detectors. However, building data-free Trojan detectors is quite challenging. Firstly, the attacker can design complex Trojan attacks. On the one hand, there are many trigger types for the attacker to choose from, including the evasive feature space triggers. For example, the natural trigger can make the Trojan model misclassify pictures of sheep in the grass as the class wolf. While for pictures where the sheep is not in the grass, the Trojan model can still correctly classify them as sheep. On the other hand, the attacker can use the class-specific strategy to make the neural Trojans even more evasive. The class-specific Trojan attack assigns one or more classes as the source classes. The Trojan model will misclassify source class samples if they are added with the trigger. While for non-source class samples, even if they are added with the trigger, the Trojan model can still correctly classify them. Such a discriminative attack is more evasive than traditional class-agnostic Trojan attacks. Secondly, in the data-free scenario, the defender has no access to any clean samples or samples with the trigger, which makes non-data-free Trojan detectors not applicable. To solve these challenges, we have some intuitions. The first intuition is that we should reverse engineer the intermediate representations of each class rather than reverse engineer the raw input. The intermediate representation is the output of one middle layer of the inspected model. The reason is that no matter what trigger type the attack chooses, the trigger pattern will be extracted into several dimensions in the intermediate representation. So analysis conducted on the intermediate representation should be applicable to whatever trigger type. The second intuition is that for either class-specific Trojan attack or class-agnostic Trojan attacks, the underlying mechanism of the Trojan model is to manipulate the priority of different features. Specifically, a Trojan model firstly extracts trigger features and normal features in the shallow layers as shown in this figure. Then, the Trojan model's last few years give the trigger feature priority over source class normal features. In this way, when the input sample contains the trigger and the source class benign features, the Trojan model will be dominated by the trigger feature and misclassify the sample. Following the second intuition, we can deduct the third intuition. A Trojan model tends to have low confidence when predicting the source class label. Besides, it tends to increase the posterior of the target class. In other words, as source class benign features have lower priority, source class benign samples have higher possibility to be misclassified into one non-target class. Such a tendency may be difficult to observe on real benign samples. The reason is that real benign samples have different feature qualities, and thus their posteriors have no regular pattern. However, such a tendency can be steadily observed on reverse-engineered intermediate representations. The reverse-engineered representations are optimized to convergence, so their feature quality is stable. Following these intuitions, we designed the methodology of FreeEagle. The first step is to choose one layer of the model as the inspected layer, for example, the middle layer of the model. This layer cuts the model into two parts, the feature extractor part and the classifier part. The following steps focus on analyzing whether the classifier part is abnormal. Secondly, for each class, we reverse engineer the dummy intermediate representation of this class in a gradient descent manner, with the optimization policy as maximizing the posterior of the corresponding class. Thirdly, for the intermediate representation of each class, we forward propagate it through the last few years of the model, that is, the classifier part of the model. Then we can obtain a posterior vector for each class. In this posterior vector, we set the element of the corresponding class to 0. In the end, the posterior vectors of all classes are combined into one matrix. The outliers in this matrix indicate the source and target classes of the neural Trojan. For example, in this matrix, the outlier indicates that there is a class-specific backdoor inside the inspected model. The outlier's position is 9, 14, indicating that the source class of the backdoor is class 9 and the target class of the backdoor is class 14. As for models chosen with a class-agnostic backdoor, here is an example of its matrix, where all the other classes except the target class is exposed as source classes. We evaluate our method on 4 datasets and 4 model architectures. We train hundreds of benign and Trojan models on each class with various trigger types and attack strategies. Both the Trojan models and the benign models achieve good performance on their original tasks. Besides, the attack success rates on Trojan models are high. That is, the neural Trojans are successfully planted into the models. Our method achieves good performance with detecting neural Trojans with patch, blending, or filter trigger, outperforming existing data-free Trojan detector. Our method even outperforms some state-of-the-art non-data-free Trojan detectors, especially for class-specific neural Trojans. Our method can also detect neural Trojans with more complex triggers. When detecting neural Trojans with the natural or composite trigger, FreeEagle's performance is better than or comparable with state-of-the-art non-data-free Trojan detectors. We also test our method against adaptive attacks. One of the adaptive attacks is posterior shaping. As mentioned in the beginning, FreeEagle is based on the intuition that for a Trojan model, the output posterior on the target class has the tendency to be higher than the posteriors on the non-target classes. Thus, the adaptive attacker can shape the training labels against this intuition, specifically for training samples with the target label in the poisoned dataset, that is, target class samples and samples with the trigger. The label is changed to the shaped soft label, where the posterior of the target class is lower than 1 but greater than 0.5. The labels of other samples remain unchanged. The experiment results show that though posterior shaping does make the Trojan model more evasive against FreeEagle. It cannot fully pass FreeEagle. As shown in the matrix, for Trojan models with posterior shaping, FreeEagle can still expose abnormal classes. There are more results and analysis in our paper. Please see it if you are interested. To draw a conclusion, we propose the first data-free Trojan detector that is able to detect complex neural Trojans, which even outperforms some non-data-free Trojan detectors. Thank you for listening.